Hi everyone, here is a intro to torque statics problem, which is probably the simplest type. So I'll start with that just to kind of give you some of the basics and some of the ideas on how this gets going. So you just have two children sitting on a teeter-totter, and first step in any kind of problem like this that we're going to need is first of all draw in FBD. So the free body diagram, if you take a look, we would have the weight of the children here. I like to use FG, right? Child 1. FG child 2 out at the end. Okay, and of course this sometimes we would call this the normal force. In this problem, they call this the force from this like pylon, I guess, upwards. And we would also have the weight of the seesaw downward. So there's basically four forces that are acting on the plank itself. Okay, all right. So once we have that labeled, we can go in and start to fill out some of the details. And with some of the details, we can see, I'm going to move this, yikes, over up here. Okay, we can see some of the details. So they have two children are shown balanced on a seesaw. Now here they said negligible mass of the seesaw. So this makes this problem a bit simpler. There are more involved problems where that plank wouldn't have negligible mass, but for now, that lets this part of our FBD, the force of gravity of the beam, the weight of the beam, be 0 in our problem. Okay, and they give us the mass of each child. They tell us the location of where the first child is sitting, and then where the second child would have to sit. Right, is the basis of the question. How far away would they have to sit in order for the seesaw to perfectly balance? All right, and then they would like to know what is the supporting force that's exerted by the pivot upward on the beam. All right, well, just like all of our forces problem, the next thing I've kind of taught you to do is do the T-chart. And in this case, obviously there's no forces horizontally, but we've got the weight of the child down, we've got the weight of the second child downward, and then the weight of, or the force on the plank upward. And in this case, we don't have a weight of the beam because they're telling us in the problem to make the assumption that, again, its mass is negligible. Okay, also in these equations, if we want to find a position, we're also going to need a torque formula. So we take the net torque about O, and the easiest place to do that is we want to eliminate the other unknown, which in this case is the force upward on the plank. So we can choose a convenient position for O that helps us eliminate that. And in this case, choosing the rotation point, and it probably seems natural to you, right about this point O, is a good place to put the torque equation. You could put it actually anywhere, but that seems kind of weird, but you're allowed to do that. And in this case, the natural place works out really well. So the net torque, there's going to be a counterclockwise torque, right, about the pivot point due to the weight of the first child. So that means that's a positive torque, and it's simply the weight force times its lever arm about O, and it makes a 90-degree angle, okay, with that lever arm, so sine 90. And the other child is doing a clockwise torque, and that's a negative torque. Okay, clockwise direction is negative. It tends to try to rotate it clockwise. And it's just the weight of that child times their lever arm, in this case also sine 90. So since we want it to be in equilibrium, there's no angular acceleration being caused here, so the forces of the torques add up to 0. All right, so putting our symbols in, we can see that we just got our symbols for the weight of the first child, their position, minus the weight of the second child, times their position, and we can solve for that position of the child. So solving for R2, we get this expression, substituting the masses given in the problem and the position of the first child, and then we have the mass of the second child and gravity, right, gives us a position of 1.3 meters. So that helps us find the location that the second child would have to be seated at, away from O, so that the balance beam would pivot. Okay, so there was one other thing which was asked of us, and that was to find the force upward on the plank that would be needed. So in this case, I have to try to move my, hold on. All right, so now I have to use my force equations to find the force P. So basically from our T-chart, we just use our Y column, and they should all equal 0, right? The plank's not accelerating upward or downward. And we can solve for FP because we know the weight of each child. and that gives us 568.4 newtons. So that's how you can use both rotation formula and the forces to find unknowns in simple kind of a torque and force problem.